Hello everyone, we will be going through about BTrees, right? So BTree is one of the most powerful tree or most commonly used tree, right? And there is actually a reason for it. So if you look at our slides, okay, the front part of the slides is an explanation of why BTrees are very useful. Okay, so to put it simple, right, in layman terms, we have learned binary search tree, we have learned AVL trees. Okay, so what you learn in all of these trees is I may have a bunch of nodes, okay, but my height is always log n, where n is the number of nodes. Okay, the problem is in the real world scenario, we need to save our tree somewhere, right? You need to save it. Okay, so you can save it inside your memory, right, which is your RAM, which is very fast, right? Or you can save it inside your hard storage, right? So we are talking about your hard disk, okay, we are talking about your SSDs and so on and so on. Okay, so you know your SSD is very fast, you know your hard disk is very slow, but you also know SSD is very expensive, right? So of course the price of SSD has dropped, right? But it is still expensive compared to a hard disk. So imagine if you're running a company with 1 terabyte of information, right? It can be information about your customer, right, about your clients and so on. So using a SSD is very expensive, right? And then you have compliance issues such as your Data Protection Act, when you're supposed to store all of the data as a backup for at least 3 months, right? So you're going to have a lot of stuff which you need to store. So when you save it in a hard disk, the problem with a hard disk is, right, if I were to draw it out, your information is only saved at one position, okay? And in your hard disk, you actually have a rigger, right? So your hard disk have to spin until what you want to access is actually where your rigger is pointing to. So each of the spin is expensive, right? Compared to your memory, you just go straight to the memory, you access it, right? On the other end, your hard disk have to spin. So imagine now, I have a collection of nodes, right? 1, 2, 3, 4, right? So my height is log n. So as I traverse from the root downwards, right, each time I go from a node to another node, I need to spin. So in total, I need to spin 4 times, right? So imagine if I have a lot of nodes, let's say it's n, right? I need to go log n times number of spins, which is a lot of spins, right? And to make it worse, each time I spin, I only access one node, right? So if there are numbers, let's say binary search tree, 7, 5, 6, 1, 11, 13, 9, 10, and 8. Right, you realize each time you spin, right, you only access one number, which is O1 operation. It's very expensive. So it comes into the motivation of a BTree, right? Instead of every node only saving one item, we will now change it to each node will save X number of items, right? So you can have 1 all the way to X. But then we realize if we say you can save 1, you are still not making use of your memory, right? So we will set a minimum, right? Each node have to save from X up to Y number of items, right? So each time we spin, right, we will access at least X number of information, right? So we are making the best use of it. That's why we have the concept of page, right? Where you spin, you get a page, you load into memory, and so on and so on. When you go into high performance computing, right, you want to put everything, right, into the memory of your graphics card, right? So as you should know by now, your graphics card have a DDR5 RAM, right, whereas most of your RAM is only DDR4, right? So here the processing is really fast. So this is the motivation about why your BTree is actually very, very important. Okay, so I've already written notes, right? So again, purpose is to make my explanation easier. Okay, we are going to use a branching factor, also known as your degree of key, right? Which tells us how much item we need to save in a node. Okay, given a degree of key, right? We are going to save any number of items in the range of key minus 1 all the way up to 2 key minus 1, right? So for example, if my degree is, let's say, 8, okay, means a node can save from 7 all the way up to 15 items. Okay, so what determines your key, right? What determines it? It depends on your machine itself, right? The amount of memory you have and so forth. So key is actually a very optimized number, right, for given machine. So in your level, you do not need to worry about choosing a suitable degree. In your assignment, would it be in your assignment sessions, right? It's historically it's not commonly found in your assignment, but always found in your exam, right? We will always provide you with a balance factor, no matter what. You can't a balance factor, a branching factor or a degree, no matter what, right? So it will be given to you. So why is the number so weird? Why is there a minus 1? Okay, because when we were to save it inside a node, right? When we were to save it inside a node, not only you need to save the item, right? So for example, here are my items 3, 5, 7, 9, right? We also need to save the link, right? So if we have 4 items, we are going to have 5 links, right? The first link will be less than 3. In the middle one will only be 4 because it's between 3 and 5, right? Let me change the number a bit. Okay, let's change it to 9 and 21. Right, then in between here is from 6 all the way to 8. And here is going to be from 10 all the way to 20. And the last part is going to be more than 21. Right, note your item are usually your key. Because they are your key, it is always unique, right? So this is why we actually have a minus 1. In fact, the balance factor corresponds with your number of link, right? Number of link, or another word for it is number of student, right? Or the degree, right? Which is why we use the term degree as well. I mean, if you search some of the syllabus online, it's somewhat interchangeable. And if I'm right in Arun's notes also use the term degree for a moment. Yeah, right, if you see here, right? So degree of key equals to 3 means at the bare minimum every node have to have 3 students, right? So if you see here, right? Here my root actually have at least 5 links, right? Just as an example. Okay. So going back to the whiteboard, okay, so how are you supposed to implement it? Okay, the way you implement it is over here, right? So given a degree of 3, right, or a branching factor of 3, we know for a given node, right, if I were to draw out a node, right, for a given node, right, here will be my key, okay, which is an array, okay, and here will be my link, right? Let's call it char, okay, will also be another array, okay. So if I want to save from 2 to 5 items, means I need to allocate an array of size 5, right? 0, 1, 2, 3, 4. Okay, And the minimum number of shards is from 3 to 6, which means I need to go 0, 1, 2, 3, 4, 5. Okay, so it will always the array for my shard is always +1. Okay, so if this is our current BTree, okay, this is how it's going to look like when you implement it, right? We are going to implement, for example, here I have a node of unknown, right? So what you're going to see is a node over here, right? So this is the root, right? And I'm going to have 0, 1, 2, 3, 4, right? 5 items. Okay, the first item is going to be 100. Then at the very same time, I'm also going to have a link, right? So this is for my children. So what I'm showing you is how you're supposed to implement it. Okay, so here will be a link to my node here. Here will link to my node here, right? So what is actually happening is the first one will be less than 100. The next one will be more than 100, right? Because I only have one item. Okay, and also as a node, right, the rule here apply to every node. Okay, with only the exception, the minimum, right, minimum doesn't apply to the root. Okay, your root is immune to the minimum, because if you think about it, if my BTree only have one item, how am I supposed to enforce a minimum of 2 items? It's impossible. Okay, so how am I supposed to visualize what you see here, right? 3, 7, 20. So it's going to be the same concept. I'm going to generate an array. Okay, 3. Wait, I can't remember my number. 3, 7, 20. Okay, so I'm going to generate an array here. Okay, 3, 7, 20. Okay, so if you notice, my size is the same because I need to allocate an array for a maximum of 5 items, right? Because key equals to 3, right? Max item equals to 2 key minus 1 equals to 5. Okay, so if I were to put numbers, it will be 0, 1, 2, 3, 4. Okay, then I'm going to have the same array, right, which is for my link or my children. Okay, so if we see here, everything is less, so it will be here, everything will be here, everything will be here, everything will be here, right? And the rest is going to be left with a none, right? So if I were to draw out the node, here is going to be one node, and here is going to be another node. Okay, so and this will be my root. Okay, now let's see what happens when we traverse, right? So let us not insert yet, it's a bit too fast. Let's try for a search for 7. Okay, so I'm going to have a pointer, right, which will be pointing here, right? Let's put I equals to 0. So my pointer is pointing here, right? The item at position I is equals to 100, right? And I know the item which I'm searching for, 7 is less than 100. So if 7 is less than 100, I'm going to follow the link of I, right? So I'm going to follow current equals to, right, current. So currently this is my current, right? Current got char I, which is 0, means I will follow this link down here. Okay, then I will repeat the process again, right? So my current is now here, right? It is now pointing here. Okay, then I'm going to repeat the process again, right? When I equals to 0, my item is 3, right? So 7 is greater than 3, I increment my I. Now I equals to 1. Right? Item at I is 7. Means I found my item. Okay? So let me change it now. Let's say instead of searching for 7, I'm searching for 11. Right? Let's say I'm searching for 11. When I equals to 0, right? Item I is 3. 11 bigger than 3. Increment my I. I is now 1, the item is 7. 11 is still bigger than 7, increment my I equals to 2, item I equals to grand key. Right, grand key is greater than 11 or 11 is less than grand key. Means I want to follow the link before I. Right, means I'm going to traverse sha I. Right, so current, so from a programming point of view, current equals to current dot sha I. Right, so I will traverse. Oops, my drawing is terrible. Okay, so I will traverse here. Okay, then I will find my 11 here. Okay, now let's see what happens if I'm searching for something else. Okay, now let's see what happens if I'm searching for something else. Let's say I'm searching for 35. Okay, if I'm searching for 35. Okay, so I equals to 0, item at I is 3, right? 35 is greater than 3, increment my I. It is 7, 35 is greater than 7, increment my I, which is grand key. 35 is still greater than 7, increment my I again. I equals to 3. But I equals to 3, as you see here, is actually none. So when item I is none, I will always traverse current I plus 1. Right? So if current run out of space, let me just scroll it here. Right, if current got item I is none, okay, current equals to current, I guess I can fit in current got sha I plus 1. Right, so I is 3. Wait, there's no plus 1. My bad. Right. So when I is 3, I will just traverse in such a way. Okay, so it's going to be very useful when your array is all full. Okay, I was going too fast, right? So if the item is none, I will traverse here, right? Why am I going to traverse here? Because everything else is going to be a none anyways. So I know this is already my last and final link. Okay. Well, one thing which I went a bit too fast is, right, if I were to erase here, imagine I actually have a few other items. Let's say here is 50, here is 80. Okay, so how you're going to do here is, if I want to implement a none, I'm going to scan here with a none, right? So my position here is just slowly for my traversal, right? In other words, I will make the length of my arrays very, very constant. So when I were to implement it, it'll be a class node, right? So it'll be self, let me define my init. Okay, self followed by key. Okay, so I'm going to have a self got key or item, right, equals to none, right, equals to none none, right, multiplied by key. Okay, no, this is cookie, right? Can self got link or sugar, right, depending whatever you're familiar with, none multiplied by cookie, right? So it will be consistent. Alternatively, right, I can maintain it at cookie minus 1, right, but I will need to program another condition here, right? So instead of if, it's going to be elif, right? Then I'm going to change here. If I greater than length of current got, since I use item, let's make it consistent, right? Current got item, right? So wait, I equals to here, right? Current equals to current dot char I. Okay, so if this part doesn't exist, this is how I avoid my array out of bounds, right, or array out of range. Else you're going to see here with a none. So choose whichever implementation which you're comfortable with. Okay, so rest assured you will never be asked to program in your exam, right? But just in case it's being asked in your assignment, you roughly know how are you supposed to implement it. Okay, so what you know now is I'm going to have a node, right? The number of items in my node, right, is in the range of key all the way. The number of items is key minus 1 all the way to key minus 1, right? This is the number of items in my node. So my question is, if I have n number of items, right? If I have n number of items, how many nodes do I need? Right? If I have n number of items, how many nodes will I require? Okay, so it's quite simple, right? Yeah, I can't find my mouse. Where's my mouse? Why did my mouse disappear? Hey. My mouse disappear. Am I? Okay. So, how many nodes do I need? Okay, so if I have number of items, I have 2 items, right? Each node have minimum, right? If my node were to, if every node were to have minimum, right, means every node will have key minus 1 items, right? If every node were to have maximum number of items, right, then each node will have 2 key minus 1 items, right? So I have 2 options, right? The first one, if every node will have minimum, it will be n over key minus 1 items, number of nodes. The other one will be n over 2 key minus 1, number of nodes, right? So the number of nodes which you have corresponds if it's minimum or maximum, but you have a very nice range for the total number of nodes, right? Number of nodes, right? So this is the range for the number of nodes. Why am I explaining of this like constraints and boundaries? Because if programming questions are not part of your exams, how your exam is able to ask you such question is through all of the properties, right? What is the property of a binomial tree? What is the property of a B tree? Okay, so it's something which is very useful for you to know what would all of your properties be, because it is something which may be asked in your exam. Okay, so you're going to notice a very interesting behavior here, right? If every node has minimum, I'm going to have more nodes. If I have more nodes, my tree is going to be taller, right? Because if I have less item, means the link is also less, right? So because the length is less, I'm going to have a corner tree. If I have maximum number of items in every node, my tree is going to be shorter. So you know the complexity of trees, right? Complexity of tree, right? Complexity of tree, right, is usually determined by the height, right? All of the height. Because you will traverse from the root all the way down to the leaf, right? When you insert, when you delete, when you search. So it will also be applied into your complexity, right? If my node all have the minimum number of items, my tree is going to be smaller. If my tree is smaller, my complexity will be higher, right? Because my height is bigger. If my tree, every node has the maximum number of items, it's going to be lesser and lesser and lesser, right? So if I were to show you an example, right? Let's say I got 3, 11, 21. Let me put t equals to 3 first. Okay, so my minimum equals to 2, my maximum equals to 5. Okay, so if everything is minimum, I can do the following: 10, 100, right? Then here is going to be like 3 and 5. Here is going to be, let's say, 30 and 50, and then let's say here is 200 and 300, right? Then here it will be 1 and 2. Let's change this to 6. Here will be 3 and 4. Here will be 7 and 8, right? Then here will be sorry, I can't fit in, right? 11 and 12, 31 and 32, 51 and 52, right? And then here will be let's say 101, 102. It will be 201, 202. It will be 301, 303, right? So if you look at the height of my tree, right, it is a height of 2, right? The number of edges. Now if I were to compress it and save 5 items, if you look at the same collection of items, right? So if I want to fit 5 items inside, how am I supposed to fit it in? So if I want to fit of my items, I guess it's going to be 100. Then here I first are. So if I want to fit 5, okay, 1, 2, 3, 4, 5, 5. Okay, so let me build it from bottom up. 1, yeah, it's supposed to be 4 and 5. Okay, 1, 2, 3, 4, 5. Okay, so this is the bottom one. Then here is definitely will require a 6. Okay, then the next set will be 201, 202, 300, then 301, 303, right? Then here I will point to 200. Okay, so I've already finished here. Right, I've already finished here. Then I need to fit in the next 5 again. So it's going to be 7. Okay, so I'm doing this live as well. Right, 7, 11, no, 7, 8, 7, 8, 10, 11, 12. Okay, then so I finished the ones here as well, right? So the next one is going to be 30. Okay, then the other side will be the same, right? It'll be 102, 102, right, and so on. Okay, so you realize once I fit in more items, my height right, is actually only 1. Okay, so how your exam usually asks you is the complexity, right? So imagine if I were to ask you in the exam now, given n items for a B tree with degree t equals to 3. No, with degree of t. Okay, what is the best and worst complexity? What is best and worst complexity? Okay, so I need to know the best is when my tree have the minimum height. The worst is when my tree have maximum height. Okay, so for me to get the minimum height means node f maximum item, and to get the maximum height it means my node f minimum items. Okay, so it comes to what I'm going to show you here now. Okay, what if every node is maximum, right? And oops, a bit go far. Yeah. Okay. What if every node have the minimum number of items, right? If every node have minimum of number of items, means the root, right, which is what you're going to see here, the root only have 1 item, right? Here will be 1 item. Because my root only have 1 item, I can only have 2 link, right? And right, if I have key, my minimum equals to key minus 1 items. Okay, which is why you see here got key minus 1 and key minus 1 item. So here I have 1 item, here I have 2, because I have 2 link, times key minus 1 item. Right, then how many links do I have below it? If I have key minus 1 items, means I have a total of key links. Here also I have key link, means I have 2 key links, and below me will still be key minus 1. Right, then if I were to repeat it, it will be key plus key number of links, right? You realize I actually increased by a factor of key. So if I were to write it out as an equation, 1 node plus 2 key minus 1, right, plus 2 key minus 1, right, because I have 2 key minus 1, the next level is going to be 4, it's going to be 2 key square, right, 2 key square times key minus 1 item in every node, and all the way up to the height minus 1. Why is it height minus 1? Why? Because if this is the height, right, this will be the height of 0, height of 1, right, means here will be key h equals to 0, right, here will be h equals to 1, h equals to 2, all the way until h equals to h minus 1. I mean, let's not use h, let's use k. Alright, k. Let's use h. H equals to 0, h equals to 1, right, h equals to 2, and here will be my k equals to h minus 1, right? So if I were to use k as the power, right, if I were to use k as the power, because I begin from 0, 1, 2, 3, 4, all the way until I reach here is h minus 1 for me to obtain a height of h. Okay, then I just factor out my 2 key, right? If I factor out, I regain my 1, I factor out the 2, I factor out the 2 and key minus 1, I'm going to left with the following equation, which is a geometric series. Simplify it, I mean, you know maths, I will be fast, right? I will come across such a form. And then once I've rearranged it, I realize my height equals to log key n plus 1 over 2, which means it's O of log base of key for n, right? So this is my maximum, this will be my maximum height, right? Because I have the minimum number of items. So for a B tree, right, for a B tree, max height equals to O of log key n. Okay, which is what you're going to see here. Now if I were to apply the same logic for my maximum, right, this is what I'm going to receive, right? Maximum means over here I got Q key minus 1 items, right? Means I'm going to have how many links? I'm going to have a total of Q key links. Okay, so the first one is for the root. My root have Q key minus 1 item. Below me, going to have Q key links, and each one of it will have Q key minus 1, right? Then right here I'm going to have Q key link, but because I have a total of Q key nodes, right? So it's Q key multiplied by Q key, that's why it's Q key square, and I repeat the process until I get Q key to the power of h. Okay, now you're going to ask why here it is h and why here is h minus 1. It's going to be the same logic, right? So if I use k, right? So if I were to add in a Q key, k equals to 0, right? So if it's to the power of 0, it becomes 1. Then here is actually to the power of 1. Here is to the power of 2, right? So in other words, my height begins from 1. Right, it doesn't begin from 0. So if you see here, I begin from 0. That's why it goes up to h minus 1. Okay, but if you see here, I begin from 1. So it's going to go all the way up to h for me to have a height of h. Right, that's why it goes up to h. Whereas in the first one, you only go up to h minus 1. Okay, so this is something which I really want you to be aware of. Okay, and it's not something which is covered in your tutorial answers. Okay, then you work on your maths, you do a little bit of magic, right? I'm going to come across the form here, right? Equals to my height equals to O of log n Q key. Okay, so if you were to compare both, right? If I were to write here, mean height equals to max item, right, equals to O log Q key n, right? So it's log n to the base of Q key. Then to get a max height, right, means I need to have minimum items in my node, right? It will give me O of log key, right, log n base of key. So you realize if you look at the bit O, right, both is actually log n. The only difference is your base, right? If you split into 2, it will be 2. If you split into 3, your base will be 3. If you split into key number of children, it will be key. If you split into 2 key number of children, it will be 2 key, right? So it's the same as your merge sort and your grid sort. Why is your base good, right? Your base is good because you split into left and right. So here is going to be the same concept. Okay, so such questions have been asked in the past before, right? And it is also what you see in your tutorial question number 2 and question number 3. Okay, so what I'm doing here is I'm actually explaining your question number 2 and explaining your question number 3, right? So I've explained what your BTree is, what is the property of a BTree, how to implement the nodes, right? So every node have an array for your key or for your items, and also another array for the children or the link, right? What is the size of your array? The size of your array will be Q key, right? Or you can do a Q key minus 1, but you require an additional programming line. Okay, so if you have time to implement it, I recommend you implement it on your own. Your lab question is just implement blah blah blah, right? That's nothing for me to discuss. Whew. So, right, question 2 and 3 is done. Your exam usually asks you in the form of question 4 and question number 5. So, having worked with Arun for like about 5 or 6 years, Arun loves trees, right? He really loves trees. Because trees are very elegant, trees are very efficient. Okay, so in your exam, one of the best questions for us to ask is to ask you to draw out a tree, right? It's totally impossible for us to ask you programming of BTrees because there are many ways to program it. There are a lot of ways to optimize it. So your exam, we will ask you question 4 and question number 5, right? Given a list of items, put it into a BTree, right? And your BTree have a branching factor. Given a BTree, remove a few items, right? Given a branching factor. So if you look at your lecture slides, right, you're going to realize a lot of explanation, right? So many freaking explanation. In fact, if I were to summarize up, if we go insert an item into a BTree, right, you have a lot of cases, right? You have quite a number of cases. Then to make it worse, when you want to delete item from your BTree, right, this is where it really annoys me. Right, you have case 1, then you have case 2A, B, and C, then you have case 3A and B, right, and then it's just a lot of the explanation around. Okay, so what I'm going to do now is I'm going to simplify everything into the table which you see here. Okay, all you need to know, right, of course this is my shortcut way of remembering it. As a fun fact, BTrees used to be in FIT3004, not 3155, and then what happened was 2004 have too many stuff, right, and BTree was removed, right, and when 3155 was introduced, BTree was placed in 3155. Okay, so I've always felt BTrees to be very annoying because you need to remember a lot of case, right, case 1A, group A, group B, group C, 3C, or whatever. So the table which I'm showing you here is a shortcut way of me remembering. Okay, insert and delete are the good operations you need to know, and always remember you can only insert in the leaf or delete in the leaf, right? If it's not a leaf, you can't do it. When my tree is empty, of course my root is my leaf, right? When my tree only have root, my root is also my leaf. Okay, then when you traverse down your tree from the root, when you insert, you cannot anchor a node when the node have maximum items. Okay, when you delete, right, when your operation is delete and you traverse through your tree, you can never anchor a node if the tree have minimum number of items. Okay, then how are you supposed to anchor if you can't anchor, right? If it's maximum, you need to perform a split. If it's minimum, you need to either borrow or you perform a merge. Okay, and this is where your equation goes in very nicely, right? If you notice, if my node have maximum, it have 2 key minus 1 items, means the number of items is always odd, right? It will either be 3 items or 5 items, right? It will, or 7, 9 is always odd. So we always have a median, and our median will allows us to split, right? So in this case of 5, it will split into the following form. Okay, which is very nice. Okay, then if you see here, you can only merge if both sibling is minimum, right? So if both sibling is minimum, means what? Is if my sibling is minimum, it will be key minus 1 plus key minus 1, right? If you add up both, you're going to get 2 key minus 1 plus, right, key whatever item it is when you merge, right? For example, if I have the following items, I need to merge it, right? So how I merge is it becomes 5 items, right? 1, 2, 3, 4, 5. So here is my minimum, key minus 1. Here is my minimum, key minus 1. here is my root or my parent, another item. When I merge it, you realize I will obtain my maximum. So it will always be in range very nicely, right? So if it's minimum, if both siblings is minimum, you can merge it in very nicely. Okay, but if one of your siblings is not minimum, you can borrow a lot of words, a lot of jargon, right? Let us do it by hand, and you're going to see it very nicely. So what you see here is your question number 4. Balance factor of key equals to 3, right? So if key equals to 3 means what? Right, my minimum item is key minus 1 will be Q. My maximum item, right, will be Q key minus 1 equals to 5. Right, very simple concept. Every node can have between Q to 5 items. So now my 3 is empty, and I insert S. So my S is going to be at my root, right, which is currently minimum. Right, but because my root is immune to the minimum rule, I don't care. Okay, next one I want to insert my Z. So I begin, oops, this should be S. Okay, I want to insert my Z. Okay, Z is greater than Z. Z is bigger than S, and wait. Okay, now I want to insert Z. Right, means I need to begin from my root. If my root maximum, my root is not maximum, means I can go into my root. Then I compare the element. Z is greater than S, means Z have to be on the right of S. Then Z will be over here. Then I finish. Okay. Then the next alphabet is G. G want to go inside the root. My root only have 2 items. Right, my root only have 2 items. So how you keep track of your item is very simple, right? When you go to the programming side of this, right, you also have an item called self.count, right? So this is where you count the number of items. So if my count is here, means count equals to 1, means I have 1 item, right? Over here, if my count is over here, means count equals to 5, means I got 5 items. Right, so you use your self-count to keep track of the number of items, if it's minimum or maximum. Okay, so now my root have 2 items. 2 items is not my maximum. I can go in. Okay, G is less than S, means I need to perform a shifting. Remember, it is an array. So, right, so let me just draw it out. I can have 5 items, right? 1, 2, 3, 4, 5. Let me put index. Okay, 0, 1, 2, 3, 4. Okay, so earlier on is S and Z. Okay, so my count is over here. Okay, so because my count is actually smaller than the maximum, right, which is 5, count equals to 2, means I can go into my root. Okay, I compare my alphabets one by one with my I. G versus S. G is smaller. Because G is smaller, I need to perform shifting. So the Z will be shifted to be here. S will be shifted here. Right, and then I'm going to put in a G. Okay. And then my count is going to be +1, it's going to be 3, it's going to be pointing here now. Okay, then I've already finished. I see it lagging. Okay, next alphabet is Y, right? So I check 3 is here less than 5, I can go into my node, right? 3 is less than 5, I can go into my node. Now I'm going to compare I. Y is greater than G, increment my I. Y is greater than S, increment my I. Right? Y is less than Z, means I need to perform a shift. So what is going to be happening here is I'm now going to shift my Z to be. Why is it lagging so much? Right? I'm going to shift my Z to be over here and put in a Y at position I, and my count is now going to +1. which will be pointing here. Okay, so I'm done with Y. Next alphabet will be B, right? 4 is here less than 5, means I can go in, right? B is less than G, right? Why am I lagging? Right, B is less than G, means I need to perform again a shift, right? Z is going to come here, Y, right? Y is going to be here, then here is going to be S, here is going to be G, and here is going to be B. Then my count is going to be increment to 5, right? Count is going to increment to 5, which will be pointing here. Okay, then I'm finished with my B. Next alphabet is N. Can I insert N? I look at my root. My root is maximum, right? My root is maximum. What happens if it's maximum? I'm now going to perform a split, right? So how I split is very simple. My median will always be count /Q, right? So 5 /Q will be Q. I will always have my median, right? So once I have my median, I know it is S. So what I'm going to do here is, right? Okay, everything to the left of my S, right? Going to create a new node, which is here, right? So I'm going to now create a new node. Okay, here will be B, here will be G. Okay, pop. Let me put some numbers 0, 1, 2, 3, 4. Everything to the right. Once again, create a new node. Pop. 1, 2, 3, 4, 5. Okay, so it'll be Y and Z. 0, 1, 2, 3, 4. Okay, then I will shift S. It's lagging so much. Right, I will shift S could be here. Okay. Then if you were to look at the link, right, this is where the link is going to be. Okay, so this is one way for you to implement it, and if you implement it recursively, it's usually fine, right? But you may come across a problem when after I split out the S may go on top. So the way I implement is I will always create a new node because it's the cleanest and it's the easiest way to implement it. Okay, then only I try to insert my hang, right? So now, right, because my count is now 1, means I can go in, right? So I is here. N is less than the alphabet S, means I go left, right? And it is not the maximum, I can go left. Can B, G, and finally I'm going to put in an N, right? So I'm now going to do it very fast, right? Because in your exam you will be drawing the following, right? First I only have S, then I'm going to have Z, then I'm going to have G, then I'm going to have Y. Okay, then I'm going to put in a B, then I'm going to put in an N. So if I want to put in an N, I will split it to B, G, Y, Z. Okay, then I'm going to traverse. N is less than S, go to the left. N is more than B, more than G, means N is going to be over L. Okay, finish. Next alphabet is D, right? Not maximum, can go into root. D is less than S, means I want to go left. Left is not maximum, I can go in. D is greater than B. D is less than D, G. So it's going to be D followed by B. Okay, finish. E, right? I go to the root is not maximum, okay. E is less than S, I want to go to the left is not maximum, go in. E is greater than B, E is greater than D, E is less than G, right? So it's going to be B, D, E, okay, which is what you're going to see here. I'm finished with E. Next one, F. F, can I go into the root? Root is not maximum, F goes in. F is less than S, means I need to go left. Can I go left? No, because here I got 5 items, which is the same as my maximum. Means I can't go left. So if I want to go left, the left have to perform a split. What is my median? My median is E, right? So E is going to come up here, right? Then this is how it's going to look like. Okay? Then my F, right, will now go here, and I'm going to put in a F, which is over here. Okay, so the concept is very simple. You can't go in if it's maximum, right? And you can only insert in the leaf. U is greater than E, U is greater than S, means I want to go right. Right is not maximum, right? So I will go here. U is less than Y, so U is going to be here. Finish. I is greater than E, I is less than S, means I need to go in between. In between only have 3 items, not the maximum. I will put in I, right? Because it's also a leaf. I is greater than F, E, F, G, H, I, right? So I is greater than G, I is less than N, so I is going to be here. V is more than E, V is SQUV, right? It's more, I go here. V, SQUV, V is after U, right? So it will be VYZ. Okay? M is more than E, M is less than S, I go here. Here is still not maximum, so greater than F, G, I, L, M, N, right? So M is going to be here. So here will be M, here will be N. Okay? Then S, right? S is greater than E, S is greater than S, go right. Right is not maximum, right? Means I can go right. S is more than U, more than V, less than Y. So it will be S, Y, Z over here. X, Y, Z over here. Okay, last one will be H. H is more than E, H is less than S. Means I want to go in between. But because it is maximum, 5 items, maximum, right? Maximum, I can't go in. So what happens if I can't go in? Split. What is my median? My median is I, right? So I is going to go up, right? Then it will be S. Okay, so it will still be here. It will now be pointing to here. Okay, and it will point to here. Then my I disappear. Okay, so when I split, means my median moves up, right? So if the branch is between E and S, means my median, I move up in between E and S. So when if you were to implement it, right, look from the array point of view, how you're supposed to do the shifting and so on, right? And since you implement it recursively, it's usually fine. Okay, then H, right? Remember just now I split before S, so I know H is, right? So H is more than E, H, I. H is less than I. So I will come here. H is more than F, E, F, G, H. H will be after G, which is what you're going to FL, right? So it is actually a very, very simple concept. Lagging. Okay, very simple concept. Okay, you can only insert at the leaf. You cannot anchor a node if the node is maximum, right? And you realize it's always an odd number. Because it's an odd number, I can always split the median up, right? Very simple concept. Let us try for clicking. Remember, you can only delete like a leaf. If it's not a leaf, you cannot delete it. Okay, then and you can also traverse if it's minimum. If it's minimum, right, you look at your sibling. If both siblings are minimum, you perform a merge. If one sibling is minimum, you perform a borrow, right? So let me go through the example here. So this is your question number 5. Key equals to Q. Means the minimum is key minus 1 is 1 item. Maximum is Q key minus 1 means it's 3 items, right? Means every node can only have either 1 Q or 3 items maximum. So if you were to look at your question number 5, okay, question number 5 wants me to delete 1, 22, and 16. 1, 22, and 16, and you need to draw it after each operation. So in your exam, right, you're required to draw it after each and every operation. It's not like how I show you where I combine everything into one, right? Because in your exam, we'll be marking 3 by 3. And it will also ensure you obtain your partial marks. Let's say if you mess up somewhere or anywhere, you will still have partial marking. Okay, so 1, 22, and 16. 1, 22, 16. Okay, so let me choose what here. 1, 22, 16. Okay, so the first item which I want to delete is 1. Okay, I go into the root, right? Can I go into my root? Yes, because my root is not minimum. It has 2 items. Means I can go into my root. Then I will compare. 1 is less than 4, means I want to go left. Right? This is the path I want to go. But can I go left? I can't, because L only have 1 item, which is the minimum. So if we only have 1 item, which is the minimum, I will look at my sibling. I do not have any sibling on the left, but I got a sibling on the right, which is 8. So what I'm going to perform here is, I look at my sibling, and my sibling is also minimum, right? So if you look at my summary here, if my sibling is also minimum, right, I need to perform a merge. So how am I supposed to perform a merge? Okay, to perform a merge, it's quite simple, right? Remember, I move here, means I'm looking at the element 4. Okay, 4 will go down, right? 4 will go down. Okay, right? 4 will go down, so 4 disappear, and both ring will be combined into 1. Okay, so what you see here is actually a node on its own. Okay, then because this is not minimum, I can now traverse in. So I forgive traverse in, and I'm nice. 1 is less than 22, means I need to go left, right? I need to go left. But because my left is minimum, I can't go left. Once again, look at the sibling. No sibling, my sibling here is 3, which is also a minimum. I need to perform a merge. So how do I perform a merge? Right, Q comes down, right, comma, and my limbs will be combined. Right, kasi like I can erase. Okay, here. So now I can traverse. 1 is found, 1 is a leaf. I can remove 1. Okay, so I am finished, and it's really, really, really nice. Okay, so I'm finished. Okay, next item is 22. Once again, begin with the root. Can I anchor my root? I can't, because my root only have 1 item, which is the minimum. So because I cannot anchor it, what is going to happen? If I cannot anchor it, what is going to happen? Right? I look for my sibling. Do I have any sibling? No, I do not have any sibling. Right? Means I can't merge with my sibling. Right? Why do I not have any sibling? Because I'm the root. Right? Your root doesn't have sibling. Your root is your parent. Right? Only nodes below the root have a sibling. So you look at the left sha and you look at the right sha, right? Because it is your root, right? So here is not minimum, here is not minimum, right? So I can perform a form of wait. Wait, did I mess up the tree? Give me a moment. Okay, I draw the tree correctly, right? 4K off, 4K off, 4K off, so off means I need to perform a merge, which is correct. Okay, I delete the run, which is correct, right? So oh yeah, correct. Blur. Okay, my root is immune to minimum. I actually forgot, right? So root immune to minimum. Okay, root is immune to minimum, but root is not immune to maximum. And the reason is because we are going to move the items downwards. Okay, I've forgotten root is immune to minimum. Okay, so 22 begin from the root. 22 is greater than 16, means I will go right. Right, means I will go right. Can I go right? Yes, I can go right because my right is not minimum, so I go right. Now I'm over here. Okay, so right, so I can go right, which is over here. Okay, so now I'm here. Then I'm going to compare 22 versus 16. Right, 22 is bigger. 22 versus 20, 22 is bigger, means I need to go right. But I can't go right because it is minimum. So if it's minimum, I'm going to look at the sibling. No sibling, sibling is also minimum, I will perform a merge. So when I perform a merge, means 22, means 20, 22, right? Then I've performed a merge. Then only I can traverse over here. So once again, 22 is more than 18, 22 is more than 20, 22 is the same as 22. 22 is already a leaf, it's not the minimum, means I can delete it. So this is the reason why you want to ensure the leaf you traverse is not minimum, right? So imagine what happened here, right? Imagine what happened if I traverse here, right? Imagine what happened if I traverse here and I remove 22. Okay? You realize my link is missing. It becomes weird. It becomes awkward, right? So the problem with anything becoming the minimum is when you delete it, the node may disappear, right? It will leave you with a link which goes nowhere, right? So which is why we do a merge and we move your 20 down. Right, so you realize your link doesn't mysteriously go nowhere. Okay, so the last item is 16, right? Begin from the root. Remember, root is immune to minimum. 16 is greater than the root, means I need to go right. Can I go right? I can't go right because 16, right, is already the minimum. So if I cannot go right because it's minimum, look at the sibling, right? My sibling here is none. My sibling here is not minimum, right? It is not minimum. So what happens if it's not minimum? If one of the sibling is not minimum, I perform a borrow, right? So what could I say by borrow, right? When you borrow something, it's the same as you performing a rotation. Okay, you're going to perform a rotation. So what's going to happen is you see this off. Okay, this off. Let me use a different bag. Off is going to come here. Okay, means off will disappear. Then 8 is going to go up. Okay, 8 is going to go up. Right, means it will disappear. Okay, so when this disappear, 5 is obviously here, right? Because 5 is after 4. But the link here is always after 8. But since 8 moves up, means, right, the link here will be established. Okay, so this is how your rotation is going to look like, right? As you see, right, 12 will move down, 8 will move up, and the link here will move here. It's the same as your rotation in your AVL tree, right? So I will rotate it in such a form. Okay, and because I'm such a form now, here is no longer minimum. Means I can traverse here, right? I can now traverse here. Okay, so I can now traverse into the position here. So I'm now here. 16 is greater than 12. 16 is the same as 16. So can we delete 16? No, because it is not a leaf. If it is not a leaf, right? If it is not a leaf, I need to find it and replace it with something else. I can replace with the king, right? But replacing it with a king, afterwards I traverse, I will come across the minimum issue, not what I want, right? So I can replace with my predecessor, or I can replace with my successor, right? But I can't replace with my predecessor because to traverse to my predecessor is a minimum, it's not possible, right? Whereas my successor is not a minimum. So I will replace with my successor. So replacing it with my successor, it will be 18, it will be 16. Then I will traverse again, right? Because it is not a minimum, right? Because it is not a minimum, I traverse, 16 is at a leaf, I remove it, and I'm totally fine, right? So here will be my final BTree. Okay, let's try to replace with my predecessor, just for fun. Okay, let's say I want to replace L, right? Can I go in? I cannot go in because L is minimum. So look at the sibling. The sibling is L and the sibling is L, right? So I will choose to rotate with the sibling on the right because it is 16. So what happens if I perform a rotation is, it will be the king. 16 is going to drop down, right? 16 is going to drop down. 18 is going to move up. Okay, and L is going to disappear. Okay, so you realize I will still traverse L and finally delete my 16. Okay, so this is why we will never ask you programming question, because for you to program it, there are a lot of ways for you to decide what is the sibling, what is your predecessor, what is your successor, and so on and so on and so on. Okay, so this is how it's going to be like, right? It's just a very simple process. So as a summary, right, this is what you need to look at. right? Let me just use a yellow highlighter. Okay, this is what you need to look at. Okay, cannot both you can only insert or delete at the leaf, cannot anchor when it's maximum or minimum, right? Except your root when you delete. Okay, then how are you supposed to resolve it, right? If it's maximum, you perform a split where the median goes up, right? And you will always have a median because the number is always odd, right? Here you look at the sibling, right? So if both sibling is minimum, you perform a merge. If one of the sibling is not a minimum, you perform a borrow. How do you do a borrow? It's in the form of rotation. Okay, so this is the entire summary for your lecture slides, right? From page number 20 all the way down until page number, right? So this is your location, right? Until your page number 58. So I summarize everything down, right? There's no need to remember case 1, Q3, Q A, Q B, Q3, 3A, 3B. Okay, but once again, I'm showing you the shortcut. If the exam ever asks you to explain, right, given a scenario, blah blah blah, you can explain it on your own, right? We have also proven your complexity. Why is your complexity log n? Because it depends on the height, right? What is your maximum height? What is your minimum height? Maximum height is log n to the base of t. Minimum height is O log n to the base of QT. Okay, so pretty much that's all, and hope it'll be useful for you, right? And I hope I summarize everything up. Implementation, nothing much. If you were to look at your lab question, practical number 8, right? That's all. Okay, and a lot of emphasis is here on your polynomial and Fibonacci heap. So make sure you're able to implement both. Okay, that's all, and bye bye. Bye bye.